Right, so now we are beginning with the first topic and first chapter of Unit 4, which is simple magnetism and magnetic fields. Let me just write that down. So first of all, when we're talking about magnets, what is a magnet? Right, so a magnet is an object that produces invisible magnetic fields or an invisible magnetic field. A magnetic field is something we'll talk about, obviously, right? Which allowing it to attract or repel other magnets or materials like metals that have like magnetic properties, such as iron and cobalt. Right, that is the definition of what a magnet is. Now, right, what is a magnet made of? So a magnet is made of metals. Right, and not all metals, right? So there's certain metals that can have magnetic properties. Only certain right, only certain metals can become or have magnetic properties or magnetic qualities, and these metals are called ferromagnets. Right, so the metals that are ferromagnets can be magnetized, right? So they can be turned into magnets, can be magnetized. Basically, they can be made into magnets. Which obviously examples are iron and cobalt, right? Why? Because when they are not magnets themselves, so when they are unmagnetized, right, they are attracted to magnets. So they have that property. Sorry, attracted to magnets. Okay, clear?
Yes.
Right. Now with magnets, right, they have poles. Let's go to a new page. Magnets have poles and they are normally, right, the convention is that they are called the N pole or the North Pole, or sometimes the North Seeking Pole, and the S pole or the South Pole or the South Seeking Pole, right?
Yes.
Now, why is it called the North Pole and the South Pole? Because if you let a magnet, right, hang loosely and freely, it will align itself roughly with the north and south pole of the earth. Right, and by that, right, the north pole of the magnet points towards the north pole of the earth, and obviously the south towards the south. Right, and this property of the magnet is what is used in compasses. So have you ever seen or used a compass?
Yes.
Right, and so it's marked NS, W, and E, so north, south, east, east, west, and then the needle in it,
Yeah.
one of the
Yeah.
needles is either red or has like some mark on it, right?
Yeah.
And so when you align that needle with the marking that says N, right? So you have the needle and right, north, south, east, and west. And so when that needle is aligned with N, so wherever you are, right? So for example, if you've turned the compass and north is over here, right? Basically, that means that if you move in this direction, you're moving in the northward direction, right? So if you sort of keep that compass, like if you want to, so that's why a compass helps in telling the direction. If you want to move south, right, and so you move it so that the needle aligns south, right? So south is over here, and so the needle is pointing south, and so you move in that direction, and you'll be moving south. Okay, so this is the basis of what makes compass. Okay, now because every magnet, everything that is a magnet has the two poles, right? There's certain properties or laws of magnetic poles, and the law is simple. Like poles repel, so they push each other away. Unlike poles attract. Right, so if you ever used a magnet, bar magnet, or a horseshoe magnet, have you ever used these?
Yeah.
Yes.
Right, and so you see they're like colored red and blue, and they have like that N and S on them, right? So if you have like two bar magnets, and what you do is you try to bring the side with the N, right? You can't make them stick together. It's like you can actually feel them pushing away, and that is the repulsion. So the similar poles, like meaning similar. So two north poles will not attract each other. They will repel each other. They will push each other away, right? Whereas if you had like a north pole and the south pole, and you bring it together, and they will immediately attract, and they'll like stick together, right? So that is uh, the law of magnetic poles, right? And the force between the magnetic poles decreases as their separation increases. So when they're far apart, right, the north is over here and like the south is over here, you can't really feel that pull as much, right? And so the attraction, the force of attraction decreases with distance, But when you bring them close together, you can actually feel them pulling each other right together, and they like stick. So that's something you obviously experienced with your toys or something, right?
Yeah.
Clear so far?
Yes.
Haram?
Yes. Yes.
Okay. The next thing they talk about are induced magnets. What this basically means is turning something that is not a magnet into a magnet. So making a magnet basically. Making a magnet using, my whiteboard is lagging, another magnet. So that is inducing magnetism or inducing a magnet. Right, so we talked about ferromagnets, right? They can either be magnets themselves for ferromagnetic materials, right? Ferromagnetic metals. And so they're either magnets themselves, if they are magnetized, or if they're unmagnetized, they're attracted to metals. So these materials, right, if they are unmagnetized and they are brought near and touch a magnet can be made out of them, right? So if an unmagnetized magnetic material, so basically a ferromagnet, right? So I'm using that term so you become familiar with it. A ferromagnet touches something that's already a magnet, right? It is brought near to, or it is just brought near to the pole, or even if you're not touching it directly, it is brought near to the pole of a magnet. Any pole, north or south, doesn't matter. That material is going to become a magnet itself. So the material will become magnetized. So it will be magnetized. Now keep in mind, this magnet that we're talking about, the one that we use to magnetize the other thing, it should be a permanent magnet. A permanent magnet is something that is always a magnet, right? Because we'll come across some, things that are temporary magnets, right? So permanent magnet, like the one we mentioned, like the ones you have in your toys and stuff, and the magnets behind those decorations you stick on your refrigerator or something, right? Those are all permanent magnets, so they're always magnetic.
Uh,
So, right, when this happens, you say that it is induced magnetism, and the material is an induced magnet. So how does this work? You have this bar magnet, right? The south pole, the north pole. And then you've got this chunk of a ferromagnetic material, let's say it's iron. So iron is ferromagnetic, and you bring it close to the north pole. What's going to happen is that, right, because you bring it close to the north pole and like poles attract, so attraction is better than repulsion, let's say. What's going to happen, or you touch it, and so because this side, the left side of this iron bar is facing the north pole of the magnet, the left side is going to turn into the south pole, and the right side is going to turn into the north pole. Okay.
yeah.
So now you have made a magnet out of something that wasn't a magnet. Okay. So you don't have pieces of iron lying around, but perhaps you do have iron nails. So what you can do is you can take a magnet, right? So this is the south and this is the north, and you can stick two nails on it. So when you stick one nail on it, right? That's supposed to be a nail. And so this is the south pole of the magnet, and this, I mean the nail, and this is the south pole, north pole of the nail, and it has been magnetized. What you do is now to check, oh, is it really magnetized? You stick 2. And so now you will see that the nails are sort of pushing each other. Why are they pushing each other? Because, right, these are the south poles of the nails, right, that are being attracted to the north pole of the magnet, and they're sticking to it. And now both of these are the north poles, and they are repelling each other. And so you will see that the nails are pushing each other apart. And you can further check this if, right, over here, you bring another magnet, right, and this is the north pole. And so what's happening is this is also north, this is also north, and this is going to increase the repulsion. And so the nails will move even further apart. And so, like, yes, so now you're saying, yes, those nails have been magnetized.
Okay.
Okay. Let me talk about permanent magnets and temporary magnets, and then I'll show you a video where this is put into practice, right? So that will obviously make the concept clearer. So depending on the substance that is being used as a magnet, the magnet can either be a permanent magnet, right, which means it stays a magnet, or it could be a temporary magnet, which means it only acts as a magnet when it's close to the other magnet. It only acts as a magnet for a short time, right? That short time being mostly when it is close to the permanent magnet. And when you remove it from the permanent magnet, it loses its magnetism. Right? So the materials that make up temporary magnets are called soft materials. Right? So these guys are like soft materials. Not in that, they're soft like wool or something. They're just called soft materials, and an example is iron. So iron is magnetic, but it's soft, so it's, it makes, sorry, wrong arrow. This is for temporary magnets, not permanent magnets. All right, so temporary magnets, soft materials like iron. Whereas if you want permanent magnets, you use what are called hard materials. And an example of that is steel. Okay, and so what you can actually do to check this out is, right, and you might have done this and you are playing with your magnets. You take a magnet, you've got the south pole and the north pole, and it doesn't matter which is which. You take, for example, iron nails, and so you have one nail and then you stick one nail to the next, right? So this is the south pole, and so this is the north and the south and the north and the south and the north and the south. So it's magnetism is being induced. And these are iron nails, right? So that's soft material. And then on the north pole, you have like paper clips. So you got one clip and like another clip and like another clip, right? And so this is the north pole, and so this is south and north and south and north and south and north, right? Because they're attracted to each other. And these are steel, and so steel is a hard magnetic substance, right? So it will make a permanent magnet. So how do we check this? It's sticking right now. As soon as I remove this nail from the bar magnet, all the other nails will fall. Why? Because it will lose its magnetism. So it was a temporary magnet. Whereas when I remove the paper clips from here, even though I've removed it, the paper clips have become magnetized, they will still stick to each other. So you'll still have that chain of paper clips joined together due to magnetism. Why? Because the material was steel and they ended up making a permanent magnet. So the magnetism was induced in both of these, right? One was temporary, the other was permanent. Now to show this and just to show induced magnetism, I'm going to share a like video. Let me put it up. Right, so here you go. It's a short, so
Here I have a bar magnet with a permanent magnetic field. When I put a soft magnetic material like iron, this paperclip, inside the permanent magnetic field, magnetism is induced in the paperclip. Look how the poles align. South to north, south to north, south to north. It looks like the maximum amount of paperclips that can be induced by this bar magnet is 3. Yeah, 3. But what will happen when I remove these induced magnets, let's see, from the permanent magnetic field? Do they keep their magnetism? No.
right. So that was rather close up, but just to give you an idea, right? So those paper clips are made of iron, and so they only made temporary magnets. Is that concept clear to you guys?
Yes. Yes.
And with that, right, I'll end this particular class, and so we can pick up from here. Next time we'll talk about magnetic fields and how to draw magnetic fields and all of that.
Okay.
Okay, and the strength of magnetic fields, and we'll move forward from there. Any questions?
No.
Okay, see you guys next class, inshallah.
Inshallah. Allah Hafiz.
Allah Hafiz.